The base rules are not complicated, really. The application can become complicated. I mean, if you think that ultimately, let's say these latest artificial intelligence super chips from NVIDIA, they are based ultimately on these basic laws, but they have, can't remember how many circuits they include, but they all follow those basic principles. Huh? So, and of course, it needs software support these days to design such kind of chip circuits as well. However, we deal with the basics, so we don't need the software. We need to understand how's it going. And we did some samples last time, so we continue with a lot of questions today, huh? So, because practice helps a great deal for those questions. And I'm just giving another circuit. Always mix that one up. The one in the middle. That should be the same. So here we go. Okay, so we have a 20 ohm resistor here, we have an unknown resistor here, and we have 10 volts in the circuit. And we have a current flow of 0.1 amps. So of course what we want to know is the PD over R. And how do we proceed for that one? What do we have to consider? What's question 5?
10 volt over 20 ohm plus R.
Coming closer. Let's say go this so step by step. So what is the basic law we apply from Kirchhoff here, which we have to consider? That could be a separate question actually as well, just to not just to warm you up on one side, but just to basically recollect what is the basic law. What would you apply here? What is the statement of the Kirchhoff law would you apply here? I mean, for the second law, obviously. But you actually already applied it partially, but it's good to state it as the law itself.
Like the potential difference equals the electromotive force.
Yep, exactly right. So, or the most simple version would be this one exactly. That we say the sum of all the EMFs is the sum of all the PDs. But that would be the shortest version at all by using the symbol for obviously voltage and for the EMF, or we can say it a bit in other words. This one means is the sum of all EMFs, and this one, of course, is the sum of all PDFs. Potentially PDs could be potential differences. So of all PDs, huh? Okay. And what now? If we apply that now into our circuit given, how do we have to formulate the sum of all EMFs?
The total EMF of all the cells.
Okay. So the EMF is how much?
10 volts.
10 volt, okay. So we can just go straight forward. Quite often in the solution, they already jump ahead. But it's good to have in one of those early questions to say, okay, let's apply that one-on-one. So we have the 10 volts is equal to what?
is equal to the sum of PDs. So
okay. So which one is the one you can just write down already, or even if you don't know the value?
So 0.1 times 20 plus
Okay.
0.1 times R.
Okay. So times, of course. So then how do we solve that?
So it's 0.1 R equals 10 minus 2.
It's 2. Yup. 0.1. Sorry, writing is a bit shaky. 0.1 R is 10 minus 2. Yup. Quite straightforward actually, which means 8. Hainsworth R is how much?
80.
80, right. Or we can write it in whatever way we want. It doesn't matter. So we can either make the inverse already, but let's do the 1 over 0.1 times 8, 80, huh? Okay, and what is the current unit of measurement?
Ohm.
Ohm, huh? Okay. And let me just go back quickly. And so we have the resistance. So Hainsworth, what is the potential difference?
So it's for the 20 ohm resistor is 20 times 0.1.
Okay, yep.
And for the R resistor, it's 80 times 0.1.
Exactly. 0.1. So we go back to 8 volt, huh? Okay, and then the cross check. I mean, of course, it's just the invert of what we just did here, but this is following our simple sum calculation. So Hainsworth, of course, we go like this, even if we want to know ultimately actually this one already. So, but in order to get this one, we need to know the unknown R, right? That's why we get the R first. And then we just go backwards again and get 8 volts. So the cross check is always very easy for those questions because how do you cross check now if your answer is correct?
Do the question the other way around.
Yeah, or you could just say let's add up the values you got, right? So for this one, you got a 2 volt, right? Because as you said, it's 0.1 times 20, so we get a 2 volt. So clearly, we can instantly see from this one without even calculating the R. We could just say, well, hey, if that is so 10 volt is obviously 2 volts plus unknown. whatever, voltage 2, for example, right? Let's say this is voltage 2. Then, of course, you get instantly voltage 2 must be 8 volt. Henceforth, of course, 8 plus 2 is 10. So that would be like the shortcut, right, to answer the question. But I like this approach, at the beginning at least, to say, okay, let's look into the EMFs. So let's write down how we calculate the EMF. Then we probably have somewhere an unknown value. Okay, R, so we better continue and solve the whole solution for R, then we know the unknown value. So we can write it actually down as well and say this is 80 ohms. So we found that value actually, or better in red because it was not known. So now we know 80 ohms. Write it again, sorry. 80 ohms. And then it's just very simple, right? Because then it's just all plus minus actually. The moment we know the voltage, we can just add them up or deduct whatever is then the unknown. Could as well be that we don't know the 10 volt, right? Of course, that would say, okay, we have one resistor with 20 ohms, one of unknown resistance, excuse me, or of known voltage, for example. Say we could say this is 8 volts, 20 ohms here. So what is the voltage for? What is the EMF, right? Or we could maybe not know this one. Then of course we would have to know other values and then get the current out of it. So there's various ways to ask these questions, obviously. Huh? But the best is to say, okay, what is the core law we apply? Kirchhoff, the sum of the EMFs equals the sum of the PDs. Hence, let's go with this one, and then in the end, you just can calculate it with the missing value. Huh? All right. And then let's do a bit more complicated one. That will go like this. So here we have a resistor. That's not very nice. Of 30 ohms. We have a source. 2 volts. We have another one up here. And resistor here. Here we have 10 ohms. 10 ohms. Okay. So here we go. Current 1. Then obviously we have something in point P, which makes the flow like that. I do like this, of course. And I3, of course, like that. So when we look at that, so that's a given one, and we have, of course, 6 volts given here as well. So we need to see how we're going to solve that, because we can utilize that to calculate, but we can utilize as well to get some ideas and say, well, we talked about loops, right? So important is to see what is the loop of the direction of the current. And when we look at that one, what is the loop of the current, or what are the loops of the current?
So for the 2V cell, it goes from current to the current 3 to back to current 2.
Okay, so like this?
Yeah.
Okay, all right. And for the other one?
It goes from current 1 to current 3 to current 3.
Okay, like this, huh?
Yeah.
Okay. Okay. So typically, of course, we would not see this one would not be given, right? So we would have to figure that out ourselves based upon, of course, the EMF, so the cells with their plus and minus, and then deduct out of that step one, in which directions are the currents flowing, which of course is this one based upon the solution here, right? I mean, and you see instantly, right? If you have two cells which are seemingly the same plus and minus, as on the same side, so to speak, it must be, and we have one in between a connector, then of course they must be in opposites of each other, otherwise it will not work. Or in other words, if there would be nothing in between, then of course we would have to, what is the purpose even of these two? That's another story then, but we don't answer that. Then we would have to see, okay, how does the current flow at that point? Okay, so question one answered, or the first important one, in which directions is it flowing? Because why do we need that, Chris? Why do we need to know in which direction the currents are flowing?
Because we have to know that there are two series in a parallel. Oh, wait, no.
Okay. Yeah. Okay. You're coming close. When you think of, I mean, there's only one point now labeled. Basically, we could label, let's do that for the sake of it, and could call that Q, right? So why are P and Q important? Or helpful, either way?
Because at point P, both currents join.
Okay, yep. And what happens in point Q?
They separate back to their own series.
Yeah, exactly. Okay, so clearly we apply Kirchhoff's first law, right, where we say in and out has to equal, right? Which makes a lot of sense, obviously. Of course, under ideal conditions. Not everything may be like that in the current, but energy-wise, of course, it makes sense. It's just that maybe some energy goes away as heat, but we don't want to make things complicated at that stage. So we say, okay, we go like this. So that's why it's so important to have a clear understanding of the direction of the current, because in any intersection point, of course, the node of a circuit, I have to know, well, okay, what's happening here? And obviously, again, this is a bit helpful. That's why they're already labeled the same indice, like current 2. And why is that like that, actually? Why does the one which is here is that one equal to that one, or vice versa? Well, actually, as we flow in this direction, we can say, why is this one I2 as well?
Because it's its own, it's it's a series.
Yeah, you may, yeah, kind of, that's correct, right? I mean, or it's just one, how to say, I mean, the whole thing is one circuit, right?
Yeah.
Right, so it's not necessary, it's kind of in series. That's why it's okay that we say it's in series, actually, especially, but they're not really two elements in that one. It's just an EMF and a resistor, a PD, right? So basically, it's the most simple of all circuits, kind of, that we just say, well, okay, we have a circuit and we have a resistor in it, and of course a source, and that's it. But we could say it's in series, kind of. We rather talk about series when we have two resistors like that. Then we rather talk about series, for example. If it's a single one, yeah, kind of, but there's only one, so they cannot be really anything. But it's not wrong at all, and it helps the thinking exactly. And thus, we of course have one source here. I mean, on the other hand, what goes out has to come back, right? So if there's I2 going out of the source or the cell, then of course I2 has to come back, otherwise it won't work. So that's sometimes a very simple indicator as well to say why these currents, or it may help then to determine other currents in the circuit eventually. Or it may not be really needed, depends a bit, but at least based upon that circuit here, you can say, well, what is leaving has to come back. That has to be identical because there's no current loss, right? That's what we assume as well in our calculations. Okay, so, and we want to determine, of course, the question is what are the various currents, right? So the I, so to speak, and I from 1 to, well, 3 in this case. So we have answered one step. So, okay, let's look into the point P. What can we say about the point P? I mean, you said it, but I just want to write it down once more. What can we say about in regards to the current related to Kirchhoff's first law?
The current towards the junction is equal to the current leaving the junction.
Yeah, okay, all right. So let's say in has to be out, which in other words means the out is clear. That's I3. And what about the in? What is the...
I1 plus I2.
Yeah, exactly. So there it has to be the sum, obviously. Exactly. So we have already one first equation, right? And as we have to determine 3 currents, how many equations do we need, Chris? Just now from you look at the basic structure of the design and say, okay, we need to determine all the currents, and we identified there are 3 currents, or given. In this case, it's more given, but we could have identified ourselves that as well. So how many equations do we have to generate most likely in order to solve all that?
Three.
Oh, I made, of course, a mistake. I'm sorry. Just realizing something must be wrong here. 3, exactly. Yeah? Exactly. So we need 3 equations. So we have done 1 equation. What would be a natural next step to get another equation? So there we used K1, so to speak. So typically you would apply K2, right? Second law. Where we go to the loops, and you can choose, of course, either this one or that one, doesn't matter. Let's say we choose this loop. So what is then the equation for that loop? According to Kirchhoff.
Sum of potential difference of the 30 ohm and 10 ohm equals to the electromotive force of 6.
Yeah, exactly. Yeah? So we can say 6 volts equals to 30 times. Do we know the resistor of that one? My bad. Sorry. Yeah, oh, I mean, I want to ask you, but I don't want to mislead you. But nevertheless, do we know the resistance? Oh, not the resistance, the PD, or how do we calculate the PD?
Well, I think we do 30I plus 10I.
Okay, yeah, the 30I, right? And which I would we use?
I1.
With the 30?
Yeah.
Right. It's no problem, Chris. It's just, you see, it's very important that we give these indices because we have 3 different currents. I mean, it's very clear. I know that you know that you have to multiply these together Same as here, of course, where you have to multiply them with each other, right? That's why it's so important to really jot it down on a diagram, because if we don't do that and we think, well, okay, I just look at the diagram, maybe with blank, so to speak, nothing given here, nothing written on it, chances are very high to make mistakes. So it's easy to go straight forward and say, okay, so we have the I3. So what about the second one?
10 times I1.
Yeah, exactly. All right, so we already have now two equations for that one. We chose the first loop, actually, or the upper loop, whatever. Oh, let's call it the upper loop. The upper loop is this one, huh? And now that we say, oh, okay, I have I2, I1, I3. So what would be, and we said we need three equations, right? So what could be the other equation or which other equation could be helpful here or easy to determine?
The other one, like
Yeah, exactly right.
two.
So 2 volts are equal to
30 times I3.
Yeah, exactly. Yeah. So very simple. So the secret is as well to blend out what is not needed, right? So okay, I don't care about that stuff because I focus on the lower loop. So this is all that counts. That's somehow the beauty of all these circuits, that you always isolate a certain part and then dig in deeper. For example, we'll see that when we talk in more detail about series and parallel ones. Then becomes even more important. They say, oh, I isolate that. That one now could be actually a much more complicated circuit on its own. But at this very moment, we simplified it. I mean, in our example, it's a resistor of 30 ohms, but it could be another circuit actually which results in the resistance of 30 ohm. That we have another parallel like that, serial, or we could even have a parallel for whatever reason. That's another story then, right? That inside the box is this one. This one is inside this box, for example, resulting in the bigger picture in 30 ohms. So that plays a lot with these bottom up, top down. Huh? So you condensate it and then talk only about this one, or then you can break down later on to the one at the bottom and say, okay, what's inside there calculated. That's a very helpful approach to make that distinction. So like here now we blend that one out and only look at this one exactly. So when you look at the equations here, what can you basically say instantly in order to start working towards the solutions? If you give that a 1, 2, and then 3. Because, yeah, please go ahead, Chris, if you have, sorry, I'll wait.
Find I3 equals 1 over 15.
Okay. Yes, no doubt. What I would suggest is in such a case is to say, do you have anything which is really every road leads to the solution. There's various ways, right? No doubt. Because you can just substitute one equation with the other and then go from there. It doesn't matter what you choose first. Good idea is usually to take the simplest one first and say, hey, wait a minute, this one is exactly the same as this one. And the beauty is it even has a value. So I can basically forget the calculation and replace it with the 2 volts, which makes then the calculation of the I1 extremely easy, right? So when I take the 2 and the 3, you will get henceforth 6 volt equals 2 volt plus 10 I1. And therefore, what is I1 therefore, Chris?
It's equals to 0.8.
Okay, yep. Sure, 0.8?
0.4, sorry.
Yeah, right, exactly. Huh? So 6 minus 2, that's it, exactly. So divided by 10. Let's make it like that. So we get 0.4 amps. Huh? So we have the first one. So in order to keep track of it, so we say I1 is 0.4 amps. Okay. All right. Now, what could be another meaningful equation instantly? Which one would you choose next? 2 or 1? Would you take this equation rather, or rather this equation as the next step?
Second.
Second, right, exactly. So I mean, of course, this example is comparatively simple because apart from this one, I mean, no, this one contains all 3 unknowns. That's really painful. That probably must be the last one to take. On the other hand, this one, of course, you can of course, that's why I said there's various ways, right? You could as well go for this one and say, well, I3 equals 2 volts divided by 30, right? Then you have I3 already as well. That would be a different approach, but quite often you rather have to substitute first. So that's why we chose that path as an example and said, okay, take this one, which is equal to 2 volts. So I can take that one out and make this equation. But of course, on the other hand, you could go straight here and say, well, if 2 volt is I30, then of course 2 volts divided by 30 is my I3, right? It's like a shortcut. And then of course I can jump directly to this one, because obviously I have 2, I have I1, I have I3, so I can directly get I2 out of it. But my point is, that would be the easiest way. Then there's probably one which is the most complicated way. And the one we do right now first is the one in between, I would say, that we say, okay, we made some rearrangements. We got I1, and now we go for this one, because out of that we can get I3. Huh? Although we could get it easier from this one.
Yeah.
But let's follow the path we've chosen and go into this one, because we, for whatever reason, we have not realized that this is the most simple one. That's not wrong. It's just a bit more complicated. That's all. And as long as we don't get points for the shortest solution and the most elegant one, so to speak, that would be more something for math people, that they, of course, look at that and say, oh, what was the best, easiest, most direct way, most elegant way to solve it? And, a bit more on the practical side, so to speak, and say, whatever way helps us to solve it, we are okay. We don't care, which is fine. All right, so what we said is that we take equation number 2, and now we have the 6 volts equal 30 I3. I1 we have, also 30 I3 plus 10 times 10 times, and that was 0.4. Huh? Okay, so which of course is obviously 4 volts. That is still 30 I3. So how do we resolve that, Chris?
6 minus 4 equals 2 volts equals 30 ohm times current.
Yep.
And
hence I3 is how much?
1/15.
Okay. And we can now we actually have to cross check and say, well, basically the same thing, right? What we have now identified is nothing else but the rearrangement of number 3, right? Which is fine. So 1/15 volt, okay. So we have that. So I3 is 1/15. That's one of those dot. So I write it down for the time being as 1/15 amp. And we of course can, this one 0.4 is 4 out of 10, 2 out of 5. So that would be 2/5 amps. Maybe we do it rather in fractions eventually. Yeah, probably do. And then we have, of course, last but not least, I1 plus I2 equals I3. So we take that equation. And the one we have not yet figured out is I2. So how is, nearly shouldn't ask, but what is the rearrangement of that one, Chris?
I3 minus I1.
Yeah, exactly, right. So I do minus I1, and thus I have the values for those. I3 is 1/15, and I1 is 2/5. So and what does that give us?
Negative. Oh, so it's -5/15, then it's -1/3.
Okay, yep. So we go good. So this would be okay. Let's see. But 1/15, right? Minus 2/5. What would that one convert to?
So 1 minus 6/15.
Okay. And we get?
-5/15.
Okay, yep. That, just to make sure, like you said, 1 minus 3, huh? So minus 1/3 amps. Huh? So it seems at first glance a bit strange, right? Why? What? Because how can there be a negative? We are not in atomic physics where we go into quarks and stuff like that, where we have the anti-electron and stuff and so on. So what does the minus mean here? Or what is the meaning of the minus amp of I2?
Going the other direction.
Okay, very simple, straight, exactly. Huh? And does that make sense?
So does this mean that the 2-volt battery is being overpowered?
When we look at it, so it's basically it's just a reflection of what we already have shown, right? Because here and here, right? So clearly the flow of the current is in this direction.
Oh, yeah,
exactly. Yeah. This one is in this direction. Huh?
Yeah.
That's all there is. So it's nothing else but the confirmation of what we implicitly kind of, or intuitively, right? We look at it and look at the loop and say, okay, this is how it goes, because this is how it goes in terms of flow through the whole circuit. So it must be like this. Interesting thing is, of course, that the current in I2, also this one, which has to be the same for this EMF, flows actually in the opposite direction of the other. It's not really plus and minus in that sense. It's more in the sense of like what you typically talk about, in which direction is something flowing, right? So that's always a bit that thing, protons, electrons, clearly we say this is a positive charge, but ultimately ever that means in physics, and this is a negative charge. That has some deeper meaning and has nothing to do with a direction, first of all. It's really the type of charge, which is ultimately not so easy to figure out what that really means in atomic physics, actually, right? But it's a good model for the time being. Whereas the plus and minus we're talking in the circuit is really a vectorial stuff. Which direction? Not more, not less. Huh? And that's why it's sometimes puzzling to get a minus current. But of course, we just keep in mind, hey, it's the opposite direction of the other one. If you would only have one current and it would be minus, something would have probably gone wrong in our calculation, right? If we just have one circuit, then suddenly come in the calculation with a negative value, like this one, but only have nothing here, just really only that one, then obviously we made the beginning wrong. Otherwise, we could not have had minus out of it. Huh? Then it's automatically in plus, so to speak. Is that okay?
Yeah.
Okay, so there's quite a few questions in many variations for the various law applications of Kirchhoff's law. But I would like to skip that. I can send you some questions. We discussed that already, but it's just a separate brief subtopic in the book, and I think that helps us to understand more about the EMF and the PD, right? In tendency, I would suggest, I don't know how your teacher handles it, but I would suggest always talk about EMF and not the electromotive force, because it's an outdated term, actually. But the principle was kept, and that's why we still call it an EMF, which makes still sense, especially in what we are just going to discuss next. But the term itself, when we explicitly say it, is actually not really in line what we now know these days of how it really works. It was basically like there must be a force which is driving these electrons, at that time of course not electrons but positive charges, through the circuit. Otherwise they would not move, which is an interesting idea and kind of easy to understand, and there's a certain truth in that, of course. That's why the EMF still stands. But how it really works is not really related to such an electromotive force. Right? This is one step too far towards mechanics, so to speak. But it was a good step in between. That's why in tendency rather just say EMF. Huh? But it may be that the teacher still uses electromotive force, so I don't want to interfere there, but just to make you aware. The point is, quite often we say, of course, if a charge, and of course the charge is 1 coulomb, right? That's what we typically use in our electric calculations. And what we say here, maybe I put it in between, or what happens to the 1 coulomb charge, is that when it goes through the EMF, it gains energy, we can say, and it loses energy as it passes through the PD. So that is a more practical way to think about it and say the EMF is like the recharger that's why the EMF came up, of course, with electromotive force, right? Like, well, there's a source of power, of force, which will move it again and again. But we rather look into the energy flow. There, electromotive force has nothing it's not to be applied as such a term. And that means, of course, that's why we, of course, can say in the end EMF equals EMF, or the PD, my bad. So if we then say one step further, look, okay, so what is 1 volt, which is a pure definition thing at the end of the day, of course. We say 1 volt is, of course, 1 joule per second, right? So, of course, there is a little bit of a link in between here. But we already talk about joules, so we talk about energy. So we talk about energy flow, and hence with the F, maybe it should be EME, electromagnetic energy. But yeah, that's a bit cringy as well. So 1 volt is actually equal to moving 1 joules, not per second, that's, sorry, 1 joules over or the energy it needs to move 1 charge. So joules per coulomb. So we say, okay, I need a certain energy to move that charge from A to B. So A to B, and we move the charge. So it's make it a small q. So that q is moved from A to B in this direction. And this is then what we say, that potential difference needs that energy to move the coulomb to the other side, the charge to the other side. So we need 1 joule in order to move 1 coulomb. And in short, we call that 1 volt. So that is the meaning of volt in that regards. So it has a bit of two-sided coin. On one side, we think of a potential difference as like a pressure source. It pressures the charges from one place to the other, because if you do not have that pressure, it can't move. So there comes a bit of a link to the old style EMF, actually, that we push it from A to B. But on the other hand, of course, it's the more modern view is then to say, well, hey, wait a minute, I need energy to move that charge, actually, which in itself is at first maybe a bit a strange concept, because on the other hand, we think that energy, of course, is or a charge contains energy as well, right? That is then what sometimes leads a bit to confusion, to say I use energy to move energy. So yes and no. So better just think of it as the charge, the one which is in its form, that as such that it can go from here to here, a physical particle, like an electron. Let's focus on the physical particle, actually. And then we say we need that energy in order to move it from A to B. And when you regard that, really, it's actually the old question in a later stage when we say, hey, is a wave, is it a particle or is it a wave? What is does it just contain the energy, or is it actually a physical particle? That is actually the origin of Einstein's considerations, ultimately, which is then going into that mc equals mc square, right? Which is another state, but just to say, so energy is related to velocity and the mass. So that's where the point of the mass comes in, and we know that a charge is a coulomb, which is a physical presence which has a mass, which is the 10 to the power of minus 27, compared to the proton of 10 to the power of minus 23. So there's the mass aspects in the foreground, and it's about then the energy needed to move that mass, but which of course is the charge at the same time. So I hope, is that so far clear, Chris?
Yeah.
And that's why we of course can say that it goes around the circuit. So that means, of course, if the energy is being needed in order to push it, it has to originate from somewhere. It helps to go over, it kind of loses it, but then it will all add up again here at the point of origin when it goes back. So and having said that, which is usually not really a question, but brings us back with the concept of EMF-PD a bit closer. The one I would like to briefly cover today to close it is when we talk about resistors, because now we have seen that resistors play an important role. Yeah, super. They play an important role in the circuits, actually. That's why we have all the considerations of the potential difference, actually, and the EMF. But we say what happens in that resistor, and any consumer is ultimately a resistor one way or the other. And there's a couple of laws we can identify. The easiest way is always to start with the series, when we talk about the serial circuit, actually. And we can, of course, say, according to the Kirchhoff law, the current in each resistor is the same, right? That we have already looked at, and say, okay, if I have the serial one like that, and this is the resistor 1, and this is resistor 2, then the current flowing through has to be the same. So anywhere is the same current, actually. And which means henceforth, when I apply the basic laws, then I can say, of course, then the voltage, which means the total without an indice, it always means the total is nothing else but the voltage 1 plus voltage 2. We just have seen that anyway from Kirchhoff's law, right? But now we apply that as a formal guideline. It's not a law per se, but it's resulting from Kirchhoff's law. This is something we have to consider. Whereas current is everywhere the same. Huh? So if we would, I don't label it on purpose now on top here as 1 and 2, otherwise it's confusing. But it's just to keep in mind they're always the same. They are add up. So this is extremely simple. When we can, of course, the beauty is that the resistance actually follows the same law as the voltage. We can prove that by simply replacing our voltage as I times R. So if that is I times R, then of course we have V1 is I times R1 and V2 is I times R2. So because it's the same current. And henceforth, if we now replace this equation with the substitute of what we just wrote, then of course I get IR equals IR1 plus IR2. And in good math, of course, I can just cancel that one out. So surprise, surprise, I get R1 plus R2. Huh?
Yeah.
So, or to write it down here in maybe C, I moved that a bit downwards. Yeah. Okay. So, and we can write the same thing here. Okay. So the key point is to start here. If you keep that in mind like that, of course, it's very obvious in parallel, in serial, the current must be the same everywhere. And the rest just adds up. Huh? The voltage adds up, and in consequence, the resistors add up. That we will use all the time again and again when we discuss circuits in more detail. Now, if you go into parallel, then of course we talk a different story. And best is to start again with the current. That makes life easy, actually. When we have I here and I here, what would you say happens to the current in a parallel circuit? If that's again resistor 1 and resistor 2. When you think of Kirchhoff, it actually comes from Kirchhoff's law.
It should be the sum.
Yeah, very good. Yeah, exactly. Well, because we can simply say, well, if I have I1 and I2, of course, I have still I1 and still I2, of course. And hence, if I look at the node here and here, then we exactly have that I splits into I1 and I2. They must be equal. What goes in must come out, and vice versa. What comes in must go out. So, as you just said, yes, it's the sum. Huh? So it's a direct follow of Kirchhoff's law. Huh? And so we can already clearly differentiate between a serial and a parallel, the most basic ones, which then are applied in myriads of complications. But it always goes back to, do I talk serial or do I take parallel? Then it's just a matter of on which level am I talking about it. We will see about that. And from Kirchhoff, we can say, yeah, of course, what goes in must come out. So I must be I. Same thing. Oh, it's always these two very basic laws which help a great deal to make the more complicated stuff. Then what do you think happens to the voltage?
It should be the sum. Oh,
Okay. Yep.
no. It should be
Yeah.
it should be so the sum of voltage on every each circuit in the parallel, like each series in the parallel circuit should equal to each other, and the main the EMF of the cell, the main cell.
Okay. So interestingly, I just see that they don't write that explicitly in the book. Okay, because it really helps. I tell you that if we talk about the voltage, right? What would be, in other words, what would be the voltage like? Resistance is a different story. But for the voltage, what will be for the voltage over V1, so V1 and V2?
They should be equal.
This should be equal, exactly. So there's that beautiful. So it's like a reverse flip. That's why, of course, over time, one will develop a deeper sense of the configuration stuff. But an easy hook is to say, I remember this one. Because this is so obvious, that has to be the same. It's like a pipe. Even that's there cannot be more water flowing or less water flowing regardless of where I am. I may have a bigger pipe here, a smaller pipe here, a tiny one here, but it's always the same amount of water flowing. It cannot change. The speed may change, but that's a question of diameter and so on. So the amount of water must be the same no matter where I am. This is this one, current same. And even if I forget about Kirchhoff, then I can just say, well, if the current is everywhere the same, the voltage has to add up. Because it's like, oh, it's one after the other. I add them up. And in consequence, the resistor adds up as well. So when I then talk about parallel, I can say, okay, it's exactly the opposite. Current is not the same anymore, it just adds up. And the same holds true for the voltage. It's not adding up anymore, it's the same. So it's just flipping it over. So what used to be a sum will become equal. Sorry, one too low. Equal. And what it was to be equal becomes the sum. So if you ever in stress in a test, then you can always deduce it again from your recall and say, okay, I start with the current, and in a serial, that's the most obvious one, it's equal. Hence, in the parallel, it's the other way around, so it's adding up. And for the voltage in serial, of course, it's adding up. It's the opposite of equal, so to speak. Henceforth, it's the same in parallel. So that's a bit like a memory bridge in order to call it. But of course, it has its logical background, so better keep it like that. Now, the voltage, the resistance is a bit more complicated. But of course, you can just come up with the same calculation like we did before. Let's just put it on the next page this time. Say, well, if this one is like that, right? Then of course I1 is the same. Must be voltage over resistance. I2 is voltage over resistance. And because I said the voltage is the same, so of course I only have to consider that one. Huh? So that's very important in the parallel circuit. So that means now, of course, if it's true that, or as it's true, as the currents are adding up, I will just make a substitution and can say, okay, in consequence, I have V over R is of course V over R1 plus V over R2, and in good math, I can substitute, delete that as well. So I get the inverse. So I get the sum of the reverse, or inverse, better said, of these two. Or we can as well say r minus 1 is r1 minus 1 plus r2 minus 1. Yeah? Same thing. Okay, so here is the fraction, or the inverse, the sum of the inverts, and of course plus. So that's a bit a special case, but can be easily deduced by just always applying the same basic rules. This one is the fundamental of the fundamental. Kirchhoff is the second one. Then I just, of course, have to figure out, that's why it's so important, well, is the voltage the same or the current? So clearly in the parallel, currents are different, but voltages are the same. That's the practical consequence. So if the currents are adding up, then all right. And as the voltage is the same, then the resistor is different, and hence in the end I get that result. So that is clearly a bit more complicated than to calculate one specific resistance, which means you revert the whole thing. And so that's why that rule is like 1 over R. It's actually 1 over R1 plus 1 over R2. And hence we have really now the fundamental laws for the resistors, and which we then can apply in a lot of examples. Okay, Chris?
Yeah.
All right. Okay, then we continue next Friday, and we do a lot of examples related to those circuits.
Okay.
All right. Okay. Thank you then, and see you in a week.
Yeah. See you.
Thanks. Bye.